Colligative properties, part one. So colligative properties are vapor pressure lowering, boiling point elevation, and freezing point depression. These are all just ways of looking at how a solute interferes with state changes. So going from a solid to a liquid by boiling or evaporating, that's the first two, or going from a liquid to a solid by freezing. So the first one, vapor pressure lowering. The main trend is as the concentration of solute increases, the vapor pressure decreases. So if I'm looking at a vapor pressure curve, vapor pressure versus time, a pure solvent is going to have a generic vapor pressure curve. As I add more solute to it, my vapor pressure curve is going to be lowered. So pink is a dilute solution and green is a more concentrated solution. There are a couple key points to remember. So remember that the vapor pressure is the pressure of the evaporated liquid. So I'm not at boiling. As the temperature increases, more of my liquid can evaporate, which is why my vapor pressure will increase. Evaporation can only occur if surface molecules have enough kinetic energy to leave, and only the solvent leaves. So in a solution, the solute stays behind, and my solvent will be what leaves. This is not looking at it over time. This is my maximum, right? Because otherwise, I get to a certain point, and as my solvent leaves, my solution becomes more and more concentrated, and so it will have a further effect. So here's a way of being able to see this. If I have a pure solvent, right? This is my solvent. I'm showing some of my solvent in larger picture so you can see it. Some of these molecules have enough kinetic energy to evaporate, but only the ones that have enough kinetic energy and are at the surface can evaporate. So if I look at my Boltzmann distribution curve here, this is my kinetic energy and my number of molecules. This is the minimum kinetic energy required to evaporate, so my green molecules, but only a few of those green molecules will be at the surface, and that's what's going to contribute to my vapor pressure. And that's where I would see my vapor pressure right here at this given temperature. If I have a solute in here, and the solute is showing the green, the solute is in pink, you can see that it's taking up space as to where the solvent would be. So the solute is in pink, and only the green, the clear circles and the green, can actually evaporate. So again, I'm at the same temperature, same minimum kinetic energy required, but because some of these molecules are pink and not green, then there are fewer molecules within my system that have enough energy to evaporate. And because this is a homogeneous solution, I not only have pink molecules here, but I also have pink molecules taking up space at the surface. There are fewer green molecules, fewer molecules of my solvent that both have enough kinetic energy and are at the surface and can evaporate. And so what's going to happen is that my vapor pressure will be lower. I will have fewer molecules evaporated at any given temperature. So if this was my given temperature here, fewer molecules, and therefore my vapor pressure will be lower. So again, only molecules at the surface that have enough kinetic energy can evaporate, and only the solvent can evaporate. The solute physically gets in the way and takes up places where I could have enough solvent molecules that have enough kinetic energy to evaporate. So as a result, at any given temperature, I will have fewer molecules evaporated, and therefore my vapor pressure curve will be lower. There are two things that I can look at, two equations. One is I can either just find the new vapor pressure by multiplying the mole fraction of my solvent times my vapor pressure of my pure solvent, or I can find the change, how much it will have decreased at any given temperature, by multiplying the mole fraction of the solute times the pure pressure of the pure substance. So if I'm looking at my solvent, if this is 100% solvent, then my new pressure will remain the same as my pure solvent because it's just pure. Similarly, if I have no solute in here, I'm multiplying this by 0, I will have no change in pressure. So that's one way of remembering which mole fraction this is. And mole fraction would be moles of solvent over total or moles of solute over total? Well, vapor pressure is related to boiling point because vapor pressure is the temperature at which the vapor pressure equals the atmospheric pressure. So if my vapor pressure curve is lowered, the temperature required to reach the vapor pressure so that it's equal to the atmospheric pressure So as the vapor pressure curve lowers, the amount of temperature required will increase. So as the solute concentration increases, the boiling point increases or elevates, hence the term BPE, boiling point elevation. And the formula that we use for that, for the equation, is delta T. How much the temperature is increased is equal to a constant, Kb, times the molality of my solution. So the Kb is a constant that's dependent on the solvent properties, the strength of the IMFs of the solvent. But this is all solvent-based. Solute doesn't evaporate, so I'm just looking at what happens to my solvent. The third colligative property is FPD, or freezing point depression. As my solute concentration increases, my freezing point goes down, or depresses. And this has to do with the fact that the solute particles get in the way of forming IMFs in the solid. So remember, when you have a solid, you really have to work hard to make sure that your IMFs are at this perfect spot. So the way the molecules are oriented with one another makes a big difference. So here, if I'm looking at these water molecules trying to form a hydrogen bond with one another, it can't because this solute particle is physically in the way. So what has to happen is that the molecules have to slow down even more and squeeze the solute out in order for the water to finally freeze. So they've squeezed the solute out. The solute particle is sad because it's no longer part of a homogeneous solution, and yay, now I can form those hydrogen bonds in a close proximity so I can make a solid. The equation is very similar to the other one. It's the change in temperature from the freezing point is equal to a constant times the molality of my solution. So that constant is unique to the strengths of the IMF in the solvent again. So each solvent has its own Kf and Kb values. So this is something that you may often see in freezing. So freezing is a way of being able to purify a substance. If you say to yourself, wow, I'm so tired of my iced coffee getting diluted with ice cubes, I'll make iced coffee cubes. So you make coffee, you pour it into ice cube trays, and you go back and there's this like little tiny ice cube surrounded by slushy coffee on the outside, and you're like, what? What's happening is that the solute, which is the coffee, gets squeezed out and you have pure ice on the inside. And as it squeezes out more and more of the coffee, the outer solution becomes more and more concentrated. So the freezing point may be lower than your actual freezer is able to deal with. This is also how salt melts ice on the road. What it does is that it gets in the way of the water molecules, forming the intermolecular forces of attraction, and it lowers the freezing point. So it may be, in terms of Fahrenheit, 32 degrees Fahrenheit or 0 degrees Celsius, but at that point there's so much salt on the road that water will actually, that solution will actually freeze at -4 degrees Celsius rather than 0 degrees Celsius. And so now what would have been frozen is now unfrozen. Now clearly it can get too cold for the salt to even do anything, because even with that solution it's reached its freezing point, which is why here in New England they don't just put salt on the road, they also put sand on the road, because the sand will just give that traction. It's not forming a solution, it's just there's physical traction there when it's too cold for the salt to melt the ice on the road. This, however, when we're talking about popsicles, this is why homemade popsicles aren't so great, because the juice gets squeezed out. So what you have to do is you have to constantly try to agitate it, which is what ice cream churners do, is that they cause the ice crystals to become so small that your tongue can't tell the difference. Oh, and when it comes to boiling point elevation, this is not why we put salt in pasta water. We're not trying to increase the temperature of the water that it boils to cook the pasta faster. Some people say that. But the saltiness of the water that would be required to achieve any meaningful increase of temperature would be so salty that the pasta would be so disgusting that nobody would want to eat it. The reason why we salt pasta water is so that the pasta tastes better. That's it. So, why molality and constants? So, colligative properties are all about how the solute interferes with the solvent behavior. It's very solvent focused. It doesn't matter what the solute is. It could be salt, it could be sugar, it could be whatever. I could be throwing sugar on the road and it would melt just like the salt would. It's really about the water itself and how it reacts to having a solution. So because of that, it uses molality. Molality is solvent based. Remember that solvent is the denominator. I want to see how much I'm putting into a fixed amount of solvent. And the KB, that's also why the KB is solvent specific, because I'm looking at the IMFs between the solvent and the solvent, how easily I can normally rise off versus if there's something interfering with that. Because of that, your solution has to be dilute. If your solution isn't dilute, then the IMFs between your solute and your solute, or between the solute and the solvent, become an issue. And so we're not talking about super concentrated solutions. Those take on a behavior all of their own, of which there's a separate branch of science for that, well, chemistry. But there is a really interesting video in the portal called Brinicles of Death, which looks at a very real-world example of what happens when you have a super concentrated solution and how much that lowers the freezing point. So again, Brinicles of Death, narrated by the great Sir David Attenborough.